This approach leads to a number of questions. So we write down the Lagrangian, we quantize it, and we just follow our nose and do what we can. First question, do we know all possible Lagrangians? Can it be that there are more Lagrangians that we can write down, more terms that we can write down that are allowed, and we haven't yet thought about them? That might look like a strange question to ask, but over the last several years, new terms were added, terms that had been missed before. So maybe there are others. Second question, do we know all the consistency conditions? Can there be more consistency conditions that have not yet been imposed? Also, sometimes two different Lagrangians lead to the same physics. That's the idea of duality. So that's a strange starting point, because it does not uniquely, it specifies the theory uniquely, but the same theory could have more than one Lagrangian. And I'll say more below. Now, when are Lagrangians good? Lagrangians are good when they're weakly coupled. So we have a theory which is almost free, and the interactions are small, and they come in three varieties. Variety number one, here the UV is short distances, and the infrared is long distances. That's the terminology. We have a free theory at short distances, and it becomes more and more strongly coupled as we come to the infrared, to long distances. And we can say that at short distances, we formulate the question. This is a question. This is what the theory does at short distances. And in the spirit of reductionism, emphasized by David this morning, we formulate what's known at short distances. We ought to find the answer is what happens at long distances. So this is the question, and this is the answer. And I put a question mark here because often it's not easy to find the long-distance behavior of the field theory. And these are some examples. The alternative in the second possibility of having weakly coupled Lagrangian is that we have a free theory at long distances. For example, 3 plus 1 dimensional electrodynamics or chiral theory of pions. And here the question mark is in the ultraviolet at short distances. So here we know the answer, and we ask ourselves, what are the possible questions that can give us this answer? And again, there could be more than one question that gives the same answer. The third possibility is that we have a family of scale invariant theories. One of them is free at one end, but then the theory becomes more and more strongly interacting as we move to the right. And we have various examples of such theories, theories that are, it's a family of scale invariant theories. Some of them are free, and one of them is free, and then the interactions become stronger and stronger. And the Lagrangian is useful. This whole way of thinking in terms of Lagrangian is good when the theory is free or the interactions are small. And it's totally useless when the interactions are large. I'd like to emphasize that the Lagrangian is not good enough. First, there's the question I've already alluded to of strong coupling. The Lagrangian is fantastic when it's weakly coupled, because then it's kind of WYSIWYG. What you see is what you get. You see the fields, that's what you have as the answer. But then when the interactions are strong, it's not WYSIWYG. You can start with one set of degrees of freedom and end up with a totally different set of degrees of freedom. And that's when quantum field theory is interesting. And it's usually hard to determine the behavior at strong coupling. I should also emphasize that whenever exact solutions are known, the way they are known and the way the solution is found is not by using the Lagrangian. There are some exceptions, but by and large, exact solutions are found not by using the Lagrangian, but by using the more abstract point of view with the operators and their correlation functions and their consistency conditions. That's how most systems in 2 dimensions were solved, in 1 plus 1 dimensions. That's also what's true within integrable systems. The Lagrangian is not a natural starting point. And then there is the notion of duality, which is extremely surprising. And I think something I'll say more later, the fact that we are surprised by duality is the fact that we don't understand it. Because once we understand something, we are not surprised when it happens. If we are surprised and say, wow, how did this happen? It shows that we don't understand it. And in addition, we have quantum field theories that we know and love, and we can prove rigorously that they cannot come from a Lagrangian. So these are strongly coupled theories that cannot come from a Lagrangian. There is no Lagrangian at shorter distances, which is free and flows to these theories at long distances. So even if you love Lagrangian and you dismiss these points, you're not going to be able to describe these theories that don't have a Lagrangian. So this is a big challenge. I would like to suggest that what all this means is that quantum field theory should be reformulated, that there must be a better way of thinking about quantum field theory. And let me review some of the arguments. First, our natural starting point based on Lagrangians that are being quantized, as I said, are not good enough. One way of saying it is that when we have a Lagrangian and we quantize it, we assume that there is a classical system, and the quantum system is obtained by quantizing the classical system. We have some classical system, we have some phase space, we quantize it, and we find the quantum field theory. These theories that don't have a Lagrangian are intrinsically quantum mechanical. They don't have a parameter like h bar that we can pretend that we make it smaller, and then the theory becomes more weakly coupled. The theory is intrinsically quantum mechanical, and it's not obtained by starting from something else, which is classical, and then later we quantize it. So that's a statement the Lagrangians are not good enough. Second, it's not mathematically rigorous. Now, this is a very peculiar thing, that we have a theory that we know is right. We show this spectacular success with so many digits. That's not a coincidence. It has had a lot of impact on mathematics with new results, new surprises in mathematics. It's clear that something very deep is going on here, and yet it's not mathematically rigorous. And every approach to make it mathematically rigorous gets stuck somewhere else. And in fact, some mathematicians say, one quote I heard is that, you guys have lots of theorems, but no definitions. So you have lots of results, but you don't know what you're talking about. I think this should be viewed as an opportunity, both for physicists and mathematicians. And I believe that if we find a rigorous formulation, it will not just be kind of being careful about details, but in fact, it will give us new insights. New insights that I think we miss, and if we have this better understanding, that would help in the future. We also have examples motivated by string theory of ideas that are generalizations of traditional local quantum field theory, like field theory on a non-commutative space. There's something called little string theory, and there might be others. That's very interesting because these are not gravitational theories. We know they exist. They come from string theory. They satisfy most of the properties we would like a quantum field theory to satisfy, but not all of them. For example, this theory doesn't have a traditional energy momentum tensor. And yet, it's almost as good as a field theory. So before I talked about theories that are traditional, good old-fashioned quantum field theories that do not have a Lagrangian, this thing is worse. This thing is worse, and yet it exists. So it's clear, it kind of screams, we don't understand something. There's something here we don't understand. Finally, we have this gauge-gravity duality, which has been dominating our field for the last 2 decades, or it's also known as ADS-CFT. So this is the ADS, and this is the CFT. And this shows that quantum field theory is dual to a theory of gravity. And finding a theory of quantum gravity is clearly a deep question, and we clearly need deep new ideas. So if we fully understand quantum field theory, we'll also understand better gravity, and that also tells us that something deep is still missing. And finally, as I said before, quantum field theory consistently surprises us. We've heard these 3 talks this morning, and these speakers covered just the tip of the iceberg of all these topological phases and new fancy phenomena in condensed matter physics, which are really surprising. It's amazing that quantum field theory could do that thing. And these new phenomena continue to come in, and we are constantly surprised by them. So that, together with duality, I would say, tells us that enormous progress, we are surprised by it. It clearly means that we don't understand deeply what's going on. There must be a deeper formulation. So with that, I'd like to thank you for your attention, and say again, happy birthday, ICTS, and keep doing the good work. If I really had to go on a limb, I would say that this separation between short distance and long distance should go away. Because the reason is this is the one thing that most of us would think this will better not go away. So that was one argument. The other argument that I can throw into the mix is the issue of the hierarchy problem, or naturalness. For many years, I believed in naturalness, I am still a believer of naturalness, but we have to face reality. The LHC has not yet found anything. So it might be that that's just the way things are. It might be that there's something the LHC misses and it's just around the corner. I would still hope that this is what's going on. But it might also mean that there's something basic about quantum field theory which would make this whole question of naturalness just go away. I have nothing to add to this, but it again speaks about these long distance and short distances. Okay, this step of going from one to the other step by step, this is what is known as the renormalization group. And this has been kind of one of the pillars of quantum field theory over the last, how many, 50 years now, give or take? Maybe I'm wrong by the counting, maybe 40 years. And this has been enormously successful. And that's the only way I can think of quantum field theory. I don't know any other way of thinking about it. And in the two ends, things simplify. But there's a beautiful story in between. And some systems that are completely solvable are solvable exactly as a function of the scale. So we know everything that's going on in between. There's no surprise there.
It seems to me that the main problem here is locality and our understanding of space and time. And the examples you gave, where we are unsure of what this framework, I like to distinguish from a theory. We have examples of particular quantum field theories that are totally understood. No problem. It's a closed subject as a theory. But as a framework, we have no idea where it leads. It includes string theory, it seems. And the ignorance is when we start, say, considering going from the infrared to the ultraviolet, an infinite domain with higher dimension operators, irrelevant operators, and we have a few examples where we can do that, like field theory in a non-commutative space-time or string theory. But it all has to do with space-time on the one hand. And it all has to do with locality. We get into... And on the other hand, as you remarked, string theory appears to be an equivalent way of describing quantum gravity, equivalent to the quantum field theories we know and understand, which suggests that dynamical space-time is really emergent. Space-time is emergent. So my feeling is that the reformulation of quantum field theory and the definition in a sense of what the framework finally is will only emerge once we learn what emergent space and time is. Newton established equations of motion for particles in a gravitational field, but it really took a lot of mathematical work and physical understanding to understand, even for single particles, not field theory, what the complete framework is. What second-order differential equations, et cetera, and that we don't know. We don't know what the. But do you agree that?
I agree with almost everything you said. First of all, I think you just endorsed the statement that a deeper understanding is needed, and it might even lead to a complete reformulation. Now, you put your finger on locality and space-time. When I responded about this long distance versus short distance, it's a cousin of the same thing. Because if you don't have locality, how are we going to separate long distances from short distances? I agree with that completely. The only thing I can slightly hedge on is that you said that you need to understand emergent space and time before this progress. I'm not sure at what order it will happen. It might be that the whole thing would be at once. I feel that this is somewhat easier than to understand the full thing. The full reformulation of the final theory of everything that explains how space emerges, how time emerges, what it means to have unitarity, because if you have emergent time, you need to understand what it means to have unitarity. So this really speaks to all these deep questions